Hey, it's Mr. Saltano, and this video is going to be on making Lewis dot structures. So the first thing we need to remember when making these is we need to remember how to find the valence electron count. So the way in which you find that is this is an abridged periodic table, and the transition metals have been cut out of the middle, so we're just looking at the taller columns on the periodic table. And within each column or group, for example, the first group is going to have one valence electron each. The second group are all going to have two valence electrons, and then when we cut across to the other side, group 13 will have 3, group 14 will have 4, etc. until we reach 8 essentially for our noble gases, our last group on the right. So the quick way to remember for this side of the periodic table is to take the column number and subtract 10 from that. So 13 will have 3, 14 will have 4. Another thing worth remembering is that the noble gases are going to have 8, like we said, and because they have 8, they're not really going to be participating in bonds because they're already stable. The exception to that is going to be helium, which only has 2, but again, already stable, not really going to make bonds. So the other elements, though, are going to make these bonds, trying to gain that stability that the noble gases have. So they're going to be making bonds explicitly in order to get that same stability. So that's the reasoning why they're going to bond in the first place, to get to that 8. And you may have heard that referred to as the octet rule, oct meaning 8, where each element is trying to have 8 electrons in its outer shell. So let's try out our first one. The first one, and by the way, at this point, if you want to pause the video, grab a pencil and paper to try these out, you can pause right now and then come back. So the first one's going to be F2. Fluorine is a diatomic, right? So it exists as 2 fluorine atoms that are bonded together. So we check the periodic table, and fluorine is in column 17, so it's got 7 valence electrons. So I'm going to take each fluorine atom and place it side by side, so 1, 2, and then I'm going to do the 7 valence electrons around each one separately, so 1, 2, 3, 4, 5, 6, 7. Now notice I strategically place those, so just a reminder that you go once around every time. But when I went around the second time, I made sure that I left the electron that was by itself nearer to the other fluorine, because that one's going to be the one making the bond, probably. And then I placed the other one. So these other ones that are around here are called lone pairs. So a pair, and a pair. They're called lone pairs. And they're not able to do bonds. So I'm going to keep those away from the other elements because they're not going to participate in bonds. Then when I place the 7 valence electrons of the other fluorine around it, 1, 2, 3, 4, 5, 6, 7. I'm going to just make sure that, again, I place this lone one in such a way that it's next to the other fluorine. But again, the rule is that you go once around. So 1, 2, 3, 4. And then we place the other ones. You don't pair them until you absolutely have to. So then we do pairing, pairing, pairing. And in order to finish this, right now each fluorine has only 7 valence electrons, which is not obeying the octet rule. So in order to give them 8, we're going to allow them to make a bond with these single electrons there. Now if we were to count, so let's see for this fluorine, 1, 2, 3, 4, 5, 6, 7, 8. He has 8 now, so he's satisfied. He's obeyed the octet rule just like the noble gases. If we check this other fluorine, he's got 1, 2, 3, 4, 5, 6, 7, and 8. He's also happy. Now notice that these electrons in the middle, in the bond, were double counted. They can't be because those electrons are shared, and that's sort of the whole point in a covalent bond, is that the electrons are shared. They can count toward each element, and that's how that element achieves octet. So these are kind of like puzzles, and we can be satisfied knowing that these are done because everyone has octet, so they must be done. So now let's try out the next one. Feel free to pause the video before any of these examples and try them out. By the way, whenever you see this looks like it might be a carbon and then an iodine. It's almost never going to be that. It's always going to be chlorine. This is actually a C and an L. So for that, we just look at number 17, chlorine. So this is going to be very similar if you want to pause and try this out. So the way that you would do this one is they each have 7. So 1, 2, 3, 4, 5, 6, 7. And again, I strategically place those to leave an electron by itself to make a bond. And then 1, 2, 3, 4, 5, 6, 7. Again, we go once around, only pairing if we have to. And then we make the bond. and both of these have achieved octet, so they're going to be happy that way. As a side note, when you get more practice with these, you may want to tidy things up a little bit to make it more like a neat Lewis structure. So for example, in many Lewis structures, they don't show the electrons that are in the bond. It's just assumed that two electrons make a bond. So we would remove those electrons. And also the bonds are typically found centered between the elements they're involved with. So we're going to move that down a little bit. So just as an example of what that would look like. So we're going to change it up a little bit. I'm going to try it for O2. So you can pause at any time. But for O2, each oxygen is going to have 6 valence electrons. And again, we're going to place them strategically. So we go once around, 1, 2, 3, 4. And then we pair them, trying to leave any alone electrons near the other element to make a bond with. So 5 and then 6. Same thing with this other oxygen, 1, 2, 3, 4. And then 5, 6. So at this point, you've probably realized we'll have to make a bond here. If we were to count the total right now, each of these oxygens would have 7 valence electrons. So we know we're not done because they're not obeying the octet rule. But also, we can't just have lone electrons. We can't just have electrons hanging out by themselves. That's never going to happen in a correct Lewis structure. So in that case, you've probably guessed we have to make a bond now with those other two. Now, if we count them, each of them will have obeyed octet, because we're going to be double counting the ones that are in these bonds. So 1, 2, 3, 4, 5, 6, 7, and 8 for that oxygen, and then we would count the same way for the other oxygen. A more neat and tidy Lewis structure for this, because the electrons are all negatively charged, these lone pairs, this lone pair, are going to repel each other. And also, we also represent bonds like this double bond here, these two bonds, as parallel to each other in the middle. So it would look more like this. It would be a neat and tidy Lewis structure that way. Okay, so another example. Nitrogen. So far we've done all these diatomic elements. Nitrogen is no exception. And so we look up nitrogen. Nitrogen has 5 valence electrons, right? It's in the 15th column. So we put them side by side, and then we place our 5 strategically. So 1, 2, 3, 4. Then we place our 5th to make a lone pair as far away from the other element as possible. And then 1, 2, 3, 4. Place our 5th far away. And you probably guessed it. Now we need to make the bonds. So a bond there. That would give each nitrogen 6. Not there yet. That would give each nitrogen 7. And then finally we would achieve octet with what's called a triple bond. So this is a triple bond between these nitrogen atoms. And again, a more tidy, cleaned up version would look more like this for our Lewis structure. Okay, so this is going to be our second to last example, carbon dioxide. It's a little bit trickier. So a couple of notes before you make any structure is you may want to try doing the dot structures individually first. For example, we may not be able to know exactly who's going to go in the center, who's going to go on the outside for this one, and what it would look like. So we do the individual Lewis structures, and for carbon, carbon has 4 valence electrons. So in other words, carbon can make 4 bonds. Every time you have a single electron, not a lone pair, but electrons that are by themselves, each of those will make a bond. And because carbon can make 4, that's kind of a rare thing. Most elements cannot make that many. So carbon will always be centered because of that, but in general, whoever can make the most bonds should go in the center because they'll be bonding with everybody else around them. If we check oxygen, oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, 6. But notice that doesn't mean it can make 6 bonds. These 2 electrons are already married and happy, and these 2 are already married and happy as well, so they can't make bonds. So each oxygen, even though it has only 6 valence, can only make 2 bonds. So because it makes fewer bonds, we're going to place those on the outside. And then I'm going to go ahead and do the same thing with the other oxygen. 1, 2, 3, 4, 5, 6. So in general, whoever can make more bonds goes in the middle. Whoever can make less bonds goes on the outside. And so you can, as you probably guessed it, we'll start bonding now. We're going to put a bond between this carbon and oxygen. And another bond, and that's going to give this oxygen octet. That's going to make that oxygen happy and satisfied. And then we look at the other oxygen carbon, and we're going to make a bond there. And then, we have sort of an issue here, and many people will make this simple error initially before it's fixed. When we're placing these electrons, we can see that he's alone, carbon and oxygen have not achieved octet, so we're not done. And you've probably realized that this electron needs to bond with that electron, but we can't just simply take a nice long line and go whoop, connect like that. We can't do that. But one thing we can do is we can move some things around as long as we don't add or remove any electrons to or from the system. So ideally this electron would have been up here instead, right? And this lone pair would have been down here. We can move those as long as you don't lose any electrons or gain any electrons in the process. So I'm just going to erase that guy, and then swap them like that, and no electrons lost or gained in the process. Now we can finish and make this last bond, and at this point everyone will have achieved octet. And just like with the other structures, there's a tidier way of doing this that looks like this. So these lone pairs will repel each other, and the bonds will be parallel and in the middle between the elements they're involved with. So that's a better way to draw it. One more example, our final example here. So this one is C2H4, or what's called a hydrocarbon. Anytime you have just hydrogen and carbon, it's going to be a hydrocarbon. And there's sort of another strategy on how to do this kind of problem. The first thing is that, just like we said before, because carbon can make so many bonds, the carbons always go in the middle. So we always put them in the middle in what's called a carbon skeleton or a carbon backbone. They're going to be making up the backbone of your molecule most of the time. And then we do the 4 valence electrons around those carbons. And we know there's going to be at least one bond between these carbons, so we're going to go ahead and place that. But now we have to ask ourselves, we don't know where these hydrogens necessarily will go, and we don't know where our double, triple, or how many bonds we'll have otherwise. But one safe bet we can make is that we can place hydrogens on each end, because no matter what, they would at least go on the end. So we start on that part. So I'm going to put a hydrogen on that end and a hydrogen on that end. From there, we can sort of try to strategize before just writing things down. We now have 4 available spaces. 1, 2, 3, 4. And we have 2 hydrogens left. So we're going to place those hydrogens together on one side of this molecule because we don't want things to we don't want it to make it so that we can't make a double or triple bond later. So if I were to try to, for example, put a hydrogen here and then another one there, that eliminates possibilities for a bond. So instead, I'm going to place them both on the bottom here. And then now we can kind of see what this is starting to shape up to look like. And then we make our bonds. So bond there, there. And then we can tell, okay, there's a double bond between these carbons in order to achieve octet for everybody. Notice, as a side note, we said each element was trying to be like the noble gases. Now carbon does that because the noble gas that's most similar to it is neon, which neon of course will have 8 in its outer shell, as most noble gases do. But hydrogen is fully happy with just having 2 because the noble gas nearest to hydrogen, most similar to hydrogen, is helium. And helium only does have 2 in the outer shell. So hydrogen will only ever have 2 in its outer shell. The hydrogen will only ever be able to make 1 bond essentially. So that will only ever be the case. And then of course a more neat and tidy Lewis structure, because these bonds will repel each other because they're all negative, will look more like this. So that's it for Lewis structures. Thanks for watching, and remember, chemistry is everywhere.